Let us now look at the topic annual payment and present worth factor. This is a popular topic, common topic which you would encounter commonly when we are paying installments for items that we purchase, monthly installments, annual installments, equal annual installments. So how do we calculate the present worth for such cases? Consider the timeline once again. Now timeline, there is a start point, and then I am going to mark ticks at equal spaced intervals. So the space between the ticks are supposed to represent the years. So let us say this time interval is 1 year, year 1. This time interval is year 2, year 3, year 4, so on up to year n. Now at the end of each year, the end of every year, I am going to pay an amount D. At the end of the second year, pay an amount D. Third year, you pay an amount D. At the end of fourth year, also similarly. So till the end of the nth year, you are paying the same amount D. Now what we need to calculate, what is the worth at this time frame. See, it is like transformation across different time frames. So let us say this is our time frame of reference now, today. So 1 year later, whatever the value of D, what is its present worth? 2 years later, whatever the value of D, what is its present worth? So on, after 3 years, what is its present worth? After n year, what is its present worth? You bring it all to the same time frame, then there you can add. So then there we algebraically add them, and then you will get the equivalent value for the present worth. So that is the principle that we are going to follow. So this D are the equal annual payments that one makes. Now Sn, we know this equation. Sn, we will use the compound interest formula. Sn, that is the value of the money after the nth year is S0 into 1 plus I to the power of n, where I is the rate of interest. So this is the future worth, and I plus 1 to the power of n is called the future worth factor. So S0 is the present value worth, 1 plus I to the power of n is the future worth factor. Now suppose we know what is the amount at the nth time. Can you calculate the present worth of that? So it is like saying that what is S0 given Sn is known. So it is just that it is equal to now Sn into 1 by 1 plus I to the power of n. So this one goes down. So 1 by 1 plus I to the power of n is called the present worth factor. S0 is now representing the present worth of the future value Sn. And 1 by 1 plus I to the power of n is present worth factor. Now let us apply this to this problem and see what is the present worth at this time frame, which is now, the present time frame. Now S0, the present worth here of this value D, which has been a payment that is made after the first year, would be D by 1 plus I to the power of 1, plus at the end of the second year you make another payment D, which is 1, the present worth present worth here would be t by 1 plus I to the power of 2. That is, I am using this equation. Then the present worth for d at the end of the third year, it will be d by 1 plus I to the power of 3. So on, if I keep doing, the installment d, which is supposed to have been paid at the end of the nth year, if it is reflected back to the present, it will be d by 1 plus I to the power of n. So all the reflections to the present time frame are added up, and that would give you the present worth, taking all the installments together. Now, simplifying it, you have d into 1 by 1 plus I, 1 plus 1 by 1 plus I square plus 1 by 1 plus I cube plus so on 1 by 1 plus I to the power of n. Now, if you look at this pattern, you see that this is a geometric progression, and this is sum to n terms of a geometric progression. And geometric progression is well known and understood. In sum to n terms, it is of the form a into 1 minus r to the power of n by 1 minus r, sum to n terms, where a is the first term and r is the common factor, which in this case is 1 by 1 plus I. Every term with respect to the previous term is different by a common factor 1 by 1 plus I. So if I apply these to this formula, I will get the sum to n terms of the geometric progression. Let us do that. So I will put a 1 by 1 plus I, 1 minus 1 by 1 plus I to the power of n, that is 1 minus r to the power of n, by 1 minus r, which is 1 minus 1 by 1 plus I. So this, on simplifying, will lead to 1 by I into 1 minus 1 by 1 plus I to the power of n. So if you substitute as for this sum here, then we will have S naught, the present worth, is equal to d into 1 by n into 1 minus 1 by 1 plus I to the power of n, and this is the present worth of all future annual installments up to nth year taken together. And this factor d is the equal annual installment. This factor here is called the present worth factor. So if an item costs S naught today and one needs to pay yearly installments for the next n years at an interest of I, interest rate of I, then the equal yearly installments D is nothing but S naught by the present worth factor. This will give you the amount D that has to be paid every year at the end of every year till the end of 10th year, so that it has a present worth of S naught. This principle can be extended to consider even inflation. We saw earlier that we know how to get the present worth with inflation included. Inflation is having the symbol F. So let us say in this timeline where each interval is 1 year, this is year 1, year 2, year 3, year 4, year n, and you are paying equal annual installments D at the end of every year, and we are interested to find what is the present worth today. What are the present worths of all the future installments, equal future installments, annual installments that one would pay? So this can be reflected to the present time, and the present worth is D 1 plus F by 1 plus I. The present worth for the second year end, the D value would be D 1 plus F by 1 plus I whole square, so on. So it would be equal to D into 1 plus F by 1 plus I plus 1 plus F by 1 plus I whole square, so on, 1 plus F plus 1 plus I whole to the power of n. So this again is a geometric progression, and it is of the form where sigma to n terms is a to 1 minus r to the power of n by r, and this can be written as a is 1 plus f by 1 plus I, which is the first term. R is the common factor, 1 plus f by 1 plus I whole to the power of n, 1 minus r. So this can be simplified as 1 plus f by I minus f. Because there is an I minus f, there is a chance of this being 0 if I is equal to f. So this equation will not be valid for I is equal to f. 1 minus 1 plus f whole to the power of n. So this is the present worth factor if I is not equal to f. If I is equal to f, each term will be 1, 1, 1, 1, add it up for n terms, so you will get value n. So this would be for I is equal to f. So if you include that into this equation, d into the present worth factor, 1 plus f by minus of all those things, this is for I not equal to f, and is equal to d into n for I is equal to f. This is the present worth factor, and for I is equal to f, the present worth factor is n. So in this way, with inflation included, also you can find what are the equal annual future installments that needs to be done for an item that is costing S naught today.